Hello guys, good morning. Good morning to all of you. Today in this session, we'll be talking about classical and quantum statistics. I'm not sure whether I am visible or not. Can you start? Good morning, Ajay. Today's class is devoted to classical and quantum statistics. So let's see how much we can cover today. Firstly, we'll start with thermal wavelength. Transition between classical and quantum regimes. Whenever you consider some gas molecules or anything, it corresponds to a thermal wavelength. So there is a formula of thermal wavelength. Thermal wavelength is represented by lambda T, and it has a value h by root over twice pi m a T. Okay, it is the wavelength of a wave packet associated with each gas particle. It may be an atom or it may be a molecule of mass m. So let me show you this pictorially. If you consider, let's say, a gas molecule, this is a gas molecule, it will also have its thermal wavelength. Let's say somewhat like this. This separation is a thermal wavelength, lambda T. This is the molecule of mass m. Now, depending on how the particles are distributed, how two particles are close to each other, we can define the classical and quantum regime. Let's say for a system to be in the classical regime, in the classical regime, the particles are well separated. So this lambda T should be much smaller than the average interparticle distance. Good morning, Morley. Interparticle distance or not. So let's say we have another particle, and it will also have its thermal wavelength. Let's say lambda T. Now, the separation between these two molecules should be much larger than the thermal wavelength of the gas molecules. means this separation, this is the separation between the two molecules, which we may denote by R0. This R0 should be much greater, or conversely this lambda t should be much smaller. Then we can say it is in classical regime. So for this case, you see R0 will be of the order of 1 upon N0. R0 is of the order of N upon 1 by 3. What is N? N is the density of particles. Okay. So you can see from here we can conclude that it is like N times R0 cube is approximately also 1. So this denotes the condition of the particles being in the classical regime. Now what will happen if this distance R0 becomes smaller and this lambda t becomes larger? What will happen according to you? You see, we can say that the gas is in the classical regime lambda t should be much smaller. So your R0 should be much greater than lambda t. Okay. Now R0 is equals to 1 upon n to the power 1 by 3. So it should be much greater than lambda t. It means n lambda t cube should be much less than 1. You can ignore this condition, this is not useful, but this holds. So when you have a system of gas particles in the classical regime, n lambda t cube should be much less than 1. Now as you go into the quantum regime, what will happen? This distance, interparticle distance, should be very less. So what may happen? If they come closer, this wave function will overlap. Okay, someone of you has already told this. So quantum effects become important when the wave functions of different particles begin to overlap. So we can say that n lambda t cube approximately equals to 1. So this defines a condition for the quantum regime. Yes, Murli. So we can say that this n lambda t cube equals to 1. It defines a curve in the t versus n curve, isn't it? If I say that this n lambda t cube equals to 1, that is n into lambda t is equals to h by root over twice pi mkt. If I write h square and if I write to the power 3 by 2. Can you write it? It is equals to 1. It basically defines a plane. It defines a line, actually defines a line in the temperature and particle density Tn plane, and that will set the difference between the quantum regime and classical regime. That sets the division between the classical and quantum regime. Now, if I plot this Tn plane, this curve on the Tn plane, what kind of graph will you get? So, let us say we are plotting T along the y axis, N along the x axis. You get a curve somewhat in this fashion. So, you can see it is becoming almost equals to 1 at some level. So, which one is classical and which one is quantum? You see, this region where n lambda t cube is much less than 1, this region is the classical region. And as you go here, your n lambda t cube becomes approximately 1. So, this portion, this region is turning into quantum. Okay. Did I understand or not? Okay. Could you get it? I hope we are now in a position to solve some problem. So, this much theory is enough for this transition between classical and quantum regime. So, you need to remember ultimately two things, that when n lambda t cube much less than 1, it defines the classical regime, and when n lambda t cube approximately becoming 1, going towards 1, it is turning into quantum regime. Now we can do a simple problem. The quantum effects in an ideal gas become important below a certain temperature Tq. When de Broglie wavelength corresponding to the root mean square, thermal speed becomes equal to the interatomic separation. For such a gas of atoms with this specification, Tq is equals to something into T to the power minus 3 Kelvin. Values of K, B and H is given to you. Can you do this problem? De Broglie wavelength becomes equal to the interatomic separation. So, lambda is equals to A. Where is Ajay? Ajay, have you come? No, Ajay came. Harry is not present. Joel. So, for quantum effects, the condition is n lambda T cube equals to 1 you can take. N is the number density, lambda is the de Broglie wavelength or thermal wavelength. De Broglie wavelength corresponding to the root mean square thermal speed, that is lambda T, becomes equals to the interatomic separation. Lambda T equals to A. And lambda is equals to, we have already told you, what is lambda? Lambda you can correlate with, and the formula is already given to you about lambda. Interatomic separation. So, okay, instead of taking A, we can take R naught, which we have used in the previous derivation. Lambda T is equals to R naught, and you know R naught is approximately 1 by n cube. N to the power 1 by 3, sorry, n cube. So, you know, in lambda T we have root over h by root over twice pi mkt. So, we can consider lambda T square. Because you have to find out T. To find out T, we have to remove the square root. You must be looking for lambda T square. So, you see, we know lambda T is equals to h by root over twice pi m k T. T is equals to TQ. So, it is TQ is equals to, you see, we have taken square h square by 2 pi m kb, this lambda t whole square. So put the values. What is the value of h? 6.626 10 to the power minus 34 whole square, 2 pi m, m is the mass is given to you 2 into 10 to the power minus 26 kg, kb you know the value 1.38 into the power minus 23 joule per Kelvin. Then 1 by lambda t square. So from here you get 1 upon lambda t square is equals to n to the power 2 by 3. So this density n is also given to you 6.4 10 to the power 25. 6.4 10 to the power 25 to the power 2 by 3. So if you evaluate this, you will get it around 0.04021. If you express it in like this, 40 into 10 to the power minus 3 Kelvin, 40.21 actually. And that's matching with option A. Let me know if you have understood this or not. Then we'll go for the next problem. Can you move forward quickly? Just note it down, then we'll go to the next problem. The next problem is quite easy problem. You know already the answer. Just give me the answer. It is necessary to apply quantum statistics to a system of particles if there is a substantial overlap between the wave function of the particles. The mean free path of the particle is comparable to the interparticle separation. The particles have identical mass and charge, and the particles are interacting. What do you think? Which one is the most suitable option for this? Option B. Option B. Are you sure? Or option A? Look, quantum statistic you want to apply means quantum effect will be prominent. Quantum realm begins when the de Broglie wavelength corresponding to the thermal wavelength, de Broglie wavelengths lambda t of the particles become comparable to what? Comparable to the size of the particle. under this condition, under this condition, the wavelength of the particle starts overlapping. Option A, na? Yes. So when you see this kind of easy questions, you have to be a little bit cautious, because the options may appear to be very close to each other. Here you can say mean free path of the particle is comparable to the interparticle sequence, but it is not about the mean free path. It is about the de Broglie wavelength. If it had given you de Broglie wavelength, then it would have been correct. But mean free path is other thing. Let's move on to our main discussion, classification of identical particles. Identical particles, it may be of two types. It may be distinguishable and indistinguishable. Now, to describe these identical particles, three statistics we have. One is the classical statistics, which is also known as Maxwell-Boltzmann statistics, and the other two are the quantum statistics. Quantum statistics include Bose-Einstein statistics and Fermi-Dirac statistics. So, initially, if you have the identical particle, it is divided or classified into two categories. It may be distinguishable, you can distinguish between the particles. So, these distinguishable particles are mainly the classical particles, big particles, which you can distinguish, and this is described by the Maxwell-Boltzmann statistics. How many n's are there in Boltzmann? 1 or 2? How many n's are there? I think 2. Another is indistinguishable. All the quantum particles are indistinguishable. And these quantum particles, they follow two types of statistics. They may be bosons or they may be fermions. If they are bosons, they will follow Bose-Einstein statistics. And if they are fermions, they will follow Fermi-Dirac statistics. So, we will discuss about this three statistics one by one. Firstly, we will start with the classical statistics, Maxwell-Boltzmann statistics. In this regard, we have to know two things. One is the Heisenberg uncertainty relation. You know it. What is Heisenberg uncertainty relation? Position and its conjugate momentum. They cannot be measured simultaneously. There is some uncertainty, and the product of uncertainty is greater or equals to h cut by 2. That is the uncertainty principle, Heisenberg. Another thing which we see is Pauli's exclusion principle. No 4 quantum numbers can be identical for two particles. Okay, so this is Pauli's exclusion principle, and Pauli's exclusion principle hinders the fermions to occupy the same energy level. Because of the Pauli's exclusion principle, you cannot accommodate more than one fermion in one level. Okay, it will depend upon the spin. Maxwell-Boltzmann statistics, the classical statistics. In short, we will call it MB statistics. It applies to classical particles where quantum particles like the Heisenberg uncertainty principle, Heisenberg uncertainty relation, and Pauli's exclusion principle do not apply. Here, I think this phrase will come before. where, like the quantum particles, Heisenberg uncertainty relation and Pauli's exclusion principle do not apply. And here the key features are: particles are identical, spinless, distinguishable and identifiable. Remember this thing. For classical particle, we imagine that they are spinless. Spin is 0. They are distinguishable. You can distinguish between them. Identifiable. Okay. There are no quantum restriction. This uncertainty relation and Pauli's exclusion principle impose some restriction on the particles, and because of that they cannot occupy an energy level as per their wish. So multiple particles can occupy the same energy state because there is no restriction posed by Pauli's exclusion principle. Pauli's exclusion principle is not valid for classical particles. No limit exists on the number of particles in the energy state. Okay. This makes Maxwell-Boltzmann statistics distinct from quantum statistics like Bose-Einstein and Fermi-Dirac. So these are basically simple things which you must know. Now, if you consider an isolated system, two conservation laws we have to keep in mind in case of Maxwell-Boltzmann statistics. Firstly, conservation of the number of particles. If you are considering an isolated system means it is made up of rigid walls. Obviously, the particles or heat cannot exchange from here, cannot go out from here. In an isolated system, total number of particles n remains constant, and you can express it in this way: n equals to sum over ni, that is equals to constant. Ni is the number of the particles in the ith energy state. What does it mean? It means that you may have different energy levels like this, different energy levels. Okay, so this energy, let's say it is having energy E1, this is E2, this is E3, and so on, let's say EI. So E1 may contain some number of particles, E2 will contain some number of particles, E3 will contain some number of particles, and let's say EI is also containing some particles. So Ni is the number of particles in the ith energy state, and if you make a sum, you will get the total number of particles, that is constant because it is enclosed in an isolated system. A change in the number of particles delta Ni, obviously there is no change in particle number, so delta Ni, which is equals to delta N equals to 0. Delta Ni is the change in the particle number in a particular energy level, and if you take the sum, you get it to be 0. So this thing I will provide in the PDF, so you don't need to write. Conservation of energy: if the particles are non-interacting, total energy U of the system will remain constant. So you see, if you have, let's say, Ni number of particles and the energy of this level is Ei, if you multiply this Ni Ei, this will give you the energy of this total energy of these many particles. So in a similar manner, we have different energy levels and different particles. If you multiply and if you add, you get a constant. That is that summation is the total energy, right? And as it is enclosed in an isolated system, the change in energy will also be 0. Okay? Delta Ni is 0, so the overall sum is also 0. Now let's calculate the Maxwell-Boltzmann statistical count. You imagine it in this way. We have various energy levels. Okay, and they are having energies E1, E2, E3, so on. Let's say En, n number of levels are there, and each level consists of particles. let's denote that E1 level is containing N1 number of particles, E2 is N2, and E3 is N3, and so on, Nn. And if I take the sum, let's say this is giving you N number of particles. So you can imagine it in this way, that initially you have total N number of particles. Total N number of particles, and you want to distribute out of those N number of particles, you want to distribute N1 number of particles in E1, N2 number of particles in E2, N3 number of particles in E3, and Nn number of particles in En. So first of all, you have to choose N1 number of particles from this total number of particles N. Again, you have to choose N2 number of particles, you have to choose N3 number of particles, and so on. Okay, so you have to choose group of particles. N1 group of particles you choose and you place it in E1. So if I calculate the thermodynamic probability, we can say that the number of ways in which the group of particles let's say N1, N2, N3 and so on up to Nn would be chosen from N particles in W1 ways, which is equals to N factorial divided by N1 factorial, N2 factorial, N3 factorial, and it will go on up to Nn factorial. And this is equals to N factorial. And you see, the way you represent sum, if you have sum of things 1 plus 2 plus 3, you write the summation sign. If you have product like things, it is represented by this symbol pi. So you are taking the product from I is equals to 1 to n. We can write it Ni factorial. Can I write it? Now let's say you have chosen N1 particles. Now each of these levels may have multiple pockets or multiple degeneracy. Let's say E1 is having degeneracy, let's say G1, E2 is having degeneracy, let's say G2, E3 is having degeneracy, let's say G3. In the same way, En is also having degeneracy, let's say Gn. So where after you choose N1 particles from a group of N particles, this is the number of ways of selecting all the group of particles. Now let's say you have chosen N1 number of particles. Now you need to distribute this N1 number of particles into this G1 number of levels. Each level is having energy E1. Okay. Now you see, Ni particles are to be arranged in Gi states, and each of this level is having the same probability. Like if you are coming with one particle, that one particle can go to this level, this level, this level, this level, equal probability. Okay. So in that case, what will happen? Each having the same It is called a priori probability. A priori probability. Of being occupied. So we are denoting that ways to be W2. This is total number of ways here. So it will be W2. Just a moment, this is not working. So what will be W2? W2 will be equals to, if you consider, let's say G1 number of state and N1 number of particles need to be arranged. So the total number of ways in which it can be done is G1 to the power N1. But same G2 to the power N2, G3 to the power N3, G4 to the power N4 and Gn to the power Nn. We can again write it in the form of the product I equals to 1 to n Gi to the power Ni. So we can say that the number of ways in which n number of particles can be distributed in the all the states will be the product of these two ways. Therefore, we can say that the number of ways in which all the n particles would be distributed among all the quantum states is W, it should be equals to W1, W2, and that is equals to, you see, n factorial will be there, n factorial, and here pi is there, here also pi there. So we are taking pi outside. Pi I is equals to 1 to n. Okay. In the numerator we will have Gi to the power Ni divided by Ni factorial. Okay. Is it clear? Let's move forward. Maxwell-Boltzmann distribution function. So, we have calculated how the particles are distributed. Now, we will calculate the probability of a particular energy level being occupied. So, this is given by Maxwell-Boltzmann distribution function f of Ei. This is the ratio of Ni by Ei. This is equals to 1 upon e to the power alpha plus beta Ei. We have already told about beta 1 by kT, and alpha we will define. So, the quantity f of Ei, what does it represent? It is basically the ratio of the number of particles, ratio of the number of particles Ni distributed to Gi states to the number of states. This quantity is called the distribution function. So, what you can conclude from here? We can say this is the average number of particles in a quantum state. It is the average number of particles per quantum state. Of the system. Look, we have n total number of particles. If I take sum over the group of particles, let us say Ni over I, so this is equals to how much? You see, Ni is equals to Gi by e to the power alpha plus beta Ei, e to the power minus alpha sum over Gi e to the power minus beta Ei. What is this thing? Gi e to the power minus beta Ei. So, we have just put the value of Ni from here, because Ni is equals to Gi by e to the power alpha plus beta Ei. Okay. So, this is nothing but the partition function. So, e to the power minus alpha into z from this we get the value of e to the power minus alpha is equals to n upon z. So, this is how alpha is defined. I hope this is clear. Give it a try. That wave functions of two identical particles in states n and s are given by phi n r1 and phi s r2 respectively. The particles obey Maxwell-Boltzmann statistics. The state of the combined two particle system is given by. Which one is the correct option? Option D will be the answer. Okay. Look, according to quantum mechanical theory of identical particles, for two particles in state n and s represented by the wave function phi n r1 and phi s r2, we have psi ns r1 r2 wave function represents the combined state of the two particles. So, for if you consider distinguishable particles, then psi ns of r1 r2 is product phi n of r1 phi s of r2. Okay. For indistinguishable particles, if you are given two fermions, then you have to apply Fermi-Dirac statistics, and the wave function, combined wave function, will be an antisymmetric wave function. Okay, so 1 by root 2 phi n r1 phi s r2 minus phi n r2 phi s r1. If it is boson, then it will be, you will get a symmetric, because plus 1 by root 2 phi n r1 phi s r2 plus phi n r2 plus phi s r1. So remember this thing. This is a like theoretical question, you know, must remember. Understood? For fermions, we will have anti-symmetric spatial wave function, and for boson, we will get symmetric spatial wave function. Now, what are the limitations of Maxwell-Boltzmann statistics? Maxwell-Boltzmann statistics, if we talk about a system on which we apply, you can consider that a number of gas molecules are contained in a box. The system which we considered in a kinetic theory of gases, you can imagine the gas particles are not exerting any force on each other. They will exert force only when they are making a scattering or a collision. Okay, the potential energy is zero, kinetic, all the energy they have are the kinetic energies. So what are the limitations? This statistics is applicable only to an isolated gas molecular system in equilibrium, when the mean potential energy due to mutual interaction between the molecules is negligible compared to the mean kinetic energy when the gas is dilute. So you see, it is applicable only to a very special case, very specific case. We can apply this MB statistics. This is a weak thing, right? If you are limited, like very limited to apply something, that is the limitation. And another limitation comes from the Gibbs paradox. The expression for MB count does not lead to the correct expression for entropy of an ideal gas. It gives paradox, and which we can resolve by dividing the expression by n factorial. We have already talked about this Gibbs paradox. चलिए go solve this problem. A Maxwell-Boltzmann gas has 3 particles in the ith state whose degeneracy is 2. Then the number of independent ways of selecting the particles in that state is. Can you do this? So we have talked about the states. So one of the states, let's say ith state, is given to you, whose degeneracy is 2 pockets. Number of independent ways of selecting the particles in the state, 3 particles. How will you distribute these 3 particles into this 2 states? Do it, guys. Option C 8, very good. As I have told you, the formula is simple. For an individual level, it is gi to the power ni, gi to the power ni. So here gi is 2, ni is 3, 8. So once you understand the theory, the problems appear to be very simple. Okay, do this problem. Consider a gas of hydrogen atoms in the atmosphere of the sun, where the temperature is 5800 Kelvin. If a sample from this atmosphere contains 6.023 × 10⁻23 of hydrogen atoms in the ground state, the number of hydrogen atoms in the first excited state is approximately 8 × 10⁻n, where n is an integer. The value of n is Boltzmann constant is given in electron volt per Kelvin. Acha, before you solve this particular problem, let me give you another portion of the theory, because without that you may not be able to solve this question. So you keep it as a note. According to MB statistics, the number of classical particles in an energy level E at temperature, let's say T, is proportional to n of E. Let's say n of E, number of particles in the energy level E. It is proportional to e to the power minus E by kT. Now I think you can do the problem. Two states you are given, ground state and the first excited state, and you know the ratio. So if I consider it to be, let's say E1, this is E2, here the number of particles will be n of E1, here the number of particles is n by E2. So n of E1, it is given to you 6.023 10 to the power 20. This is Avogadro's number. Number of hydrogen atom in the first excited state is 8 10 to the power n. So here what is the value of n? That is what you have to find out. And hydrogen atom is given to you, so we can easily find out E1 and E2. Can you do this? It's a very interesting problem. I think you should be able to do it. Give it a try. Murli, Ajay, vantage point. And I have provided enough or sufficient hints to solve this problem, and you should be able to do it. What is U1? Energy of the hydrogen atom, you know, it is minus 13.6 by n square electron volt. If we put n equals to 1, then E1 is minus 13.6 electron volt. If you put n is equals to 2, you get the first excited state, minus 13.6 by 2 square electron volt. It is how much? Minus 3.4 electron volt. Yes, Ajay. Now we know that number of particles in a particular energy level, let's say E, it is proportional to exponential minus E upon kT. So we can say that number of particles in E1 by number of particles in E2, it will be equals to e to the power minus E1 by kT. Temperature is same, right? E to the power minus E2 by kT. This is given to you 6.023 10 to the power 23. This is given 8 10 to the power n, and this is equals to e to the power. You see, if you take minus common, E1 minus E2 upon kT we can write, and E1 minus E2 divided by kT. So what it will produce? Look, exponential E1 minus E2 by kT. So here we can put the values. Minus E1, so it becomes 13.6, right? Minus minus plus, plus E2, so minus 3.4. Let's say, let's keep it in electron volt. divided by kt. kt. Okay. What is kt? Boltzmann constant is this 8.617 10 to the minus 5 electron volt. 8.617 10 to the power minus 5 electron volt per Kelvin. Okay, let's keep it in. Let's write it exponential. So what we are left with? T. T is how much? 5800 Kelvin. Electron volt per Kelvin is there, and here it is 5800 Kelvin. So this Kelvin getting cancelled, electron volt getting cancelled. So what you are left with? 6.023 10 to the power 23 divided by 8 into 10 to the power n. And if you calculate this, what value are you getting? I need a calculator. Where is the calculator? Mr. Calculator. धूल जम गया है दोस्तों. Are you getting it? 20.409. So 20.409 is like 730131299.7. So 10 to the power n equals to 6.023 10 to the power 23 divided by 8 into 7.30 into number गिनो 1 2 3 4 5 6 7 8 8 है ना. What are you getting? I'm approximately getting it. Approximately, we can write 10 to the power 14. So by comparing, 10 is 14. देखो, you will get it eventually. I have just calculated. N is 14. I think I would like to tell you, you download the calculator, get calculator. You will go to Play Store and you can calculate, get calculator. Whenever you solve physics problems and all, you should be practicing it in the get calculator, because in the NET exam also, as well as in the get exam, similar calculator will be provided. So if you can make a habit of using that calculator, it will be better, because in that calculator calculating exponential and root is a little bit tricky. Okay, you need to be habituated with that. Okay, let's go to the next statistics, Bose-Einstein statistics. So here, you know, there will be no restriction imposed by Pauli, but Heisenberg uncertainty principle will be applied, because bosons are quantum mechanical particles. So here particles are identical, indistinguishable. While the Heisenberg uncertainty principle applies to bosons, they will not obey Pauli's exclusion principle. Means you can incorporate, you can provide as many bosons as possible in a particular energy state. As a consequence of one, there exists a number of quantum states for a given energy level. Because of two, any number of bosons may occupy any given quantum states. There is no priori restriction, there is no theoretical limitation in this regard. What are bosons? Particles having spin angular momentum 0, h cut, 2 h cut, 3 h cut means integer multiples of h cut. They will obey bosons, Bose-Einstein's statistics, and called bosons. Wave function is symmetric, as I told you, 1 by root over 2 phi n r1 phi s r2 plus phi n r2 phi s r1. Wave functions are symmetric on interchange of the coordinates of two bosons, spatial plus spin. Photons has spin 1, phonon has spin 0. They are all integers, you can see. Spin is the magnitude of angular momentum. Spin angular momentum actually. So photon has spin 1. It means its spin angular momentum is 1 h cut. H cut is like the unit. The way you give 1 kg, 2 kg, kg is the unit. Same. Deuterons has spin 1. Pi mesons have spin 0. Alpha particles He4 nucleus with a spin 0. Now Bose-Einstein statistical count. This is what you have to remember. Is a thermodynamic probability for Ni indistinguishable particle or boson distributed among Gi quantum states. What will be the thermodynamic probability? It means if you are given, let's say, an energy level which has, let's say, Gi degeneracy, into how many ways you can distribute Ni bosons, Ni number of bosons into this Gi number of states. That is given by Ni plus Gi minus 1 Cni. Okay, you can remember this, Ni plus Gi minus 1 Cni, and you know the formula of combination, right? Ni plus Gi minus 1 factorial divided by whatever terms is there, Ni factorial, head minus tail. So Ni plus Gi minus 1 minus Ni, so that is Gi minus 1 factorial. You know the formula, right? NCN if you have, you know, head factorial, this is head, this is tail. Head factorial divided by tail factorial into head minus tail factorial. This is the formula of combination, right? Same thing has been considered here. Ni plus Gi minus 1 Cni. So Ni plus Gi minus 1 factorial, head factorial divided by tail factorial, Ni factorial, n minus n, head minus tail. So Ni plus Gi minus 1 minus Ni. So Gi minus 1 factorial. Ni is the number of bosons in the ith energy level. This is the ith energy level. Gi is the number of quantum states in the ith energy level. So degeneracy you can say. Now if you consider a system, there may be other states as well, right? If instead of a single energy level, if there are multiple levels, so for a system there will exist multiple energy levels. In that case you have to just take the product. Total thermodynamic probability for the system for n number of energy levels will be, this is for a single level. If you take the product I equals to 1 to n, then that will give you the total thermodynamic probability for the system. The product runs over all the n energy levels, and W is the total number of ways to distribute all the n particles among all the energy levels. Okay, and this is very straightforward. You need to remember this. So if you revise for Maxwell-Boltzmann, what you have for a single energy level having, let's say, degeneracy Gi, the probability was Gi to the power Ni for single particles. Now, if you consider the whole system, then we have some modified formula, which is this: n factorial into I equals to 1 to n gi to the power ni by ni factorial. Remember, this is for the whole system, and gi to the power ni factorial, this is for a single level. In the same way, for MB statistics, you see, Bose-Einstein, this one ni plus 1, ni plus gi minus 1 c, this is for a single level. For all the levels, we have to take a product. Let me give you some problem. The number of ways in which n identical bosons can be distributed in 2 energy levels came in June 2012. Do it. Do it quickly, guys. A, B, C, D. Which one is the answer? Number of ways in which n identical bosons needs to be distributed into 2 energy levels. So G is equals to 2. N is equals to n. Tell me quickly, what is the answer? Ni plus Gi minus 1 C Ni. Okay. N plus 2 minus 1 C N. N plus 1 C N. N plus 1 factorial by n factorial into 1 factorial. So n plus 1 into n factorial divided by n factorial. N plus 1. Let's move to the next question. Consider a system having 3 energy levels with energies 0, 2, 3 with respective degeneracies 2, 2, 3. 4 bosons of spin 0 have to be accommodated in this level so that the total energy of the system is 10 E. Number of ways in which it can be. Very good question. 3 energy levels you are given. One is 0, 2E, 3E. Degeneracies are 2, 2, 3. 2, 2, 3. Yes, option A. So G is equals to here 2, 2, 3. 4 bosons of spin 0 have to be accommodated in this energy level such that total energy is 10 E. So, in how you can accommodate 4 bosons so that total energy becomes 10 E. How many bosons will you keep in 0 level? How many bosons you will keep in 2E level? How many bosons will you keep in 3 level? How we can make it 10? If you keep, let's say, 2 bosons in 3, so 3 into 2, 6 E, the remaining 2 bosons in 2E, then what is the total energy? 10 E. Is there any other possibilities by which you can do that? No. If you keep 3 bosons in the 3 into 3, 9. 1 is not, E energy level is not there, so that is not possible. If you keep all the 4 bosons in 2E, that is not also possible. 4 into 2, 8. So the next 2E is not, will not get. So this is the only possibility, right? If you want to make the total energy of the system to be 10 E, you have to take 2 bosons. You have to keep 2 bosons in state 3 and 2 bosons in state 2E. Number of ways in which it can be done, number of ways is multiplicative. Let's say if you want to, for this, let's say the number of ways is W1, for this number of ways W2. The total number of ways will be W1, W2. Tell me the answer. I have just done significant portion of it. You tell me the answer quickly. Why product? Look, because this is the formula I. Ni plus Gi minus 1 E Ni. Product on I. Here 3 energy levels are there, but only 2 are being occupied. Tell me the answer quickly, guys. What are you doing? Option C, 18. Very good. So let's say we are applying it for this second level. Okay, for this level. So here, what is the number of particles? N is 2. Degeneracy is 2. Minus 1. C, Ni. Number of particles is again 2. Product. Next, for this one, number of particles is 2. Degeneracy is 3 minus 1. C, number of particles is 2. So this is 4 minus 1, 3 C2 times 5 minus 1, 4 C2. 3 C2 means 3 factorial divided by 2 factorial into 3 minus 2, 1. 4 factorial divided by 2 factorial into 4 minus 2 factorial is 2 factorial. So 3 factorial is 3 into 2 divided by 2, 4 into 3 into 2 divided by 4. So see what is cancelling, what is remaining. 3 into 3, 9 into 2, 18. Understood? I think you will now be able to solve any question you get. Now let's quickly talk about Bose-Einstein distribution function. The way we had our Maxwell-Boltzmann distribution function, here also we will have the Bose-Einstein distribution function. Probability for the energy level EI being occupied, it is a ratio of the number of particles by the number of states. So this is 1 by e to the power alpha plus beta EI minus 1. This is the Bose-Einstein distribution function. This is also sometimes called Bose factor. Let's solve this problem. 3 particles are to be distributed in 4 non-degenerate energy levels. The possible number of ways of distribution for distinguishable particles and for identical bosons respectively are. Do it quickly. You know all the formula now. Which option are you getting, guys? Tell me quickly. We have 3 particles, so n is equals to 3, are to be distributed in 4 non-degenerate energy levels, so G is equals to 4. The possible number of which for distinguishable particles. C you are getting, very good. For distinguishable particles, it will follow MB statistics. So here number of ways will be G to the power n. So 4 to the power 3, 64. Now if you consider the second case for identical bosons. For identical bosons, which formula will be used? W is equals to Ni plus Gi minus 1C Ni. Okay, here one level, so we are replacing Ni by N, Gi by G. So 3 plus 4 minus 1 C3, 7 6 C3. 6 factorial by 3 factorial, 3 factorial. So 6 into 5 into 4 into 3 factorial divided by 3 factorial, 2, 2, 10, 20, 64 and 20. I hope this is clear. Next, go to this last problem for the day. Yes, this is the last problem for today. An ideal Bose gas is confined inside a container that is connected to a particle reservoir. Each particle can occupy a discrete set of single particle quantum states. If the probability that a particular quantum state is unoccupied is 0.1. Unoccupied, remember this. So the particle state is occupied will be 0.9. Then the average number of bosons in that states. Actually, this is the easiest problem. Probability for a particular state with energy, let's say EI, you know, this is f of EI. So probability of not being occupied is how much? 1 minus f of EI. This is given to you 0.1. So probability of being occupied is 1 minus 0.1 means 0.9, and 9 means 9 by 10, and that is, you see, Ni by Gi, you can say. So this is the average number of bosons in that state, right? So that is 9. Average number of bosons in that state is 9. Can you say that? It is like, you don't get confused. One energy level is 1. It is, let's say, 9-fold degenerate or 10-fold degenerate. What is the average number of particles in a particle in this state? 9, na? Option B. Is it clear now? So we are stopping here. If you have any question, you can ask. In the next class, we have only one statistics left, that is Fermi-Dirac. In the next class, we will be covering that Fermi-Dirac statistics. Let's end the session here. Thank you very much. If you are new to this channel, please subscribe the channel and don't forget to like the video. Okay, like the stream. And if you are interested in taking this top 100 most important topics course, you can take it. The link is given in the description. Thank you guys. Thank you very much. See you in the next class. Bye bye. Take care.